This scientific paper focuses on the development and characterization of antimicrobial polymers, APs, with different architectures, specifically linear and Bottlebrush copolymers. The authors highlight the importance of controlling various factors such as amphiphilic balance, molecular weight, dispersity, sequence, and architecture in the development of successful APs. While many previous studies have focused on linear copolymers, the authors argue that APs with more advanced architectures, such as Bottlebrush copolymers, show improved antimicrobial activity. The researchers have recently developed multivalent Bottlebrush APs that exhibit improved antibacterial and hemocompatibility profiles when compared to their linear counterparts. However, the underlying reasons for the superior biological activity of these Bottlebrush APs are not fully understood. Therefore, this study aims to investigate the physicochemical properties that govern the differences in activity between linear and Bottlebrush architectures. The researchers use a combination of spectroscopic and microscopic techniques to analyze the physicochemical properties of the copolymers and their interactions with bacterial membrane models. They compare the solvation, thermo-responsiveness, and facial amphiphilicity of the linear and Bottlebrush copolymers. They also examine the secondary conformation and binding mechanism of the copolymers to membranes. The authors emphasize that understanding the physicochemical properties that contribute to the improved activity of Bottlebrush APs is crucial for further enhancing their performance. The ultimate goal is to design APs that can effectively combat antimicrobial resistance, which is a global public health threat due to the misuse of antibiotics and the limited number of new antibiotic agents in development. Overall, this study aims to provide insights into the structure-activity relationship principles governing the antimicrobial activity and toxicity profile of APs. By investigating the physicochemical properties of linear and Bottlebrush copolymers and their interactions with bacterial membranes, the researchers hope to contribute to the development of more effective and selective antimicrobial strategies. SEC curves of linear macromonomer S40 and Bottlebrush copolymer BS40 in aqueous eluent were obtained using poly-vinyl pyridine (PVP) as calibration. The SEC analysis confirmed the successful deprotection and purification of the polymers. A molecular weight, Mn, of 3,600 grams mol/1 was obtained for linear S40 using PVP calibration, whereas an Mn of 33,000 grams mol/1 was obtained for BS40 using the same calibration. The moles calibration, which is more appropriate for polymers with nonlinear architectures, resulted in an Mn of 100,000 grams mol/1 for BS40. These results indicate that the Bottlebrush copolymer has a higher molecular weight compared to the linear copolymer. The average degree of polymerization, dP, of BS40 was inferred to be 28. Which is close to the targeted dP of 25. FTIR spectra of S40 and BS40 dissolved in D2O-phosphate buffer and DMSO were analyzed to investigate the differences in hydration and solvation between the linear and Bottlebrush architectures. The spectra showed signals in the region of interest ranging from 1700 to 1400 cm1, which corresponded to C=O stretch vibrations and NH bending, CN stretching modes. Small differences were observed between the spectra of S40 and BS40, indicating that the polymerization process did not significantly affect the individual structures of the monomers. The differences in spectra suggested that BS40 had a more defined and stabilized structure due to intra-brush hydrogen bonding interactions, which were limited sterically in S40. Additionally, the spectra of BS40 dissolved in DMSO showed a lower intensity of C=O oscillators compared to S40, indicating a loss of hydrogen bonding to the solvent. These findings suggest that the Bottlebrush architecture of BS40 promotes a more stable secondary conformation and solvation behavior compared to the linear architecture of S40. FTIR spectra of S40 and BS40 dissolved in D2O buffer were recorded at different temperatures to investigate the thermal behavior of the polymers. The spectra revealed a phase transition in S40, marked by a complete and irreversible disappearance of vibrational modes at around 57 degrees Celsius, which could be attributed to the dehydration of the hydrophobic repeating unit, NIPOM. In contrast, BS40 showed a mostly reversible decrease in the intensity of vibrational modes, indicating a less pronounced and reversible thermal transition. These results suggest that the Bottlebrush architecture of BS40 has a more stable conformation and a less pronounced thermal response compared to the linear architecture of S40. Dye leakage assays using E. coli liposomes and RBC liposomes were performed to investigate the membrane permeability induced by S40 and BS40. Both polymers showed concentration-dependent dye leakage from E. coli liposomes, with similar EC50 values. However, the overall dye leakage activity of BS40 seemed to be increased compared to S40. On the other hand, neither S40 nor BS40 induced significant dye leakage from RBC liposomes. These results suggest that both polymers have a higher affinity for bacterial cell-like membranes compared to RBC liposomes, potentially due to their interaction with the negative intrinsic curvature of bacterial membranes. QCMD measurements were performed to investigate the polymer-membrane interaction using supported planar bilayers made of phospholipids as model membranes. The results showed a rapid and higher binding of BS40 to the surface compared to S40. The mass per area and chain density per surface area were higher for BS40 compared to S40, indicating a higher number of brush chains adsorbed to the surface. The polymers remained strongly bound to the surface in PBS, but desorbed when flushed with Müllick water. The desorption rate was slower for BS40 compared to S40. These findings suggest that the Bottlebrush architecture of BS40 has a higher binding tendency and a stronger interaction with the membrane surface compared to the linear architecture of S40. DLS measurements were performed to investigate the aggregation of E. coli liposomes induced by S40 and BS40. Both polymers induced concentration-dependent aggregation of the liposomes, with S40 inducing larger aggregates compared to BS40. These results suggest that the linear polymer S40 has a higher tendency to induce random aggregation of liposomes compared to the more stable and less solvated Bottlebrush polymer BS40.